what is a metal? And of course, here we have just what heavy metal did you say Edwards is researching, so we can only imagine. So there's 92 elements in the periodic table, and how do we think about these? So, here's one download of, metals in pink and metalloids, whatever that is, in yellow, and non-metals in blue. And the way we denote elements is the atomic number is the number of protons, and we give that Z, and that's denoted X, which is the symbol here with a subscript before with the Z there. So for example, hydrogen, 1 hydrogen, 29 copper, 92 uranium. That's the convention. And, of course, we go from the lightest to the heaviest. So it's pretty daunting, but Tom Lehrer can help us get our brains around the periodic table. So we'll listen to this.
Now, here's a song I always get requests for, but I can't understand for the life of me why. It's simply the names of the chemical elements set to a Gilbert and Sullivan tune. I think the only reason I do it is to see if I still can. We'll try. There's antimony, arsenic, aluminum, selenium, and hydrogen, and oxygen, and nitrogen, and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, actinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, bromine, lithium, beryllium, and barium. I left out one, actually. A new one was discovered since the song was written. It's called Lawrencium. So those of you who are taking notes can write it down in your programs. There's holmium and helium and hafnium and erbium and phosphorus and francium and fluorine and terbium, manganese and mercury and molybdenum and magnesium and dysprosium and scandium and cerium and cesium and lead, praseodymium and platinum, plutonium, palladium, promethium, potassium, polonium, tantalum, magnesium, titanium, tellurium, and cadmium and calcium and chromium and curium. There's gold and californium and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, kryptonium, radon, xenon, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard. And there may be many others, but they haven't been discovered. Thank you. You may be interested to know that there is an older, much earlier version of that song, which is due to Aristotle, and which goes like this. There's earth and air and fire and water. Life was much simpler in those days, yes.
Okay, just so you know, you will be asked to recite that on the midterm. No, I'm just kidding. Don't panic. But anyway, that sort of gives you a feel for how complicated the issue is. I mean, that's all of the elements. I don't think he would do the metals simply because we've got so many different definitions of what is a metal. So here's the astronomer's view of the metals. So basically, astronomers look at the stars and they divide the periodic table into metals and non-metals. And the metals are everything heavier than helium. And we laugh at that, but you may find that in this course, that's a pretty good definition. We'll get you'll see more. All right, so here's the chemist's view of metals from the internet. And what you can see are the very brightly colored periodic table, all kinds of colors. And you can see, what do we got here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different ways of calling them. Now, if you look at the things, you might say, okay, they're the metals, maybe would include alkali metals. That's lithium, that first row. Alkaline earths, if alkaline metals are a metal, then the alkaline earths next to them should be too. And then there's the transition metals, which oftentimes are the metals we see in our daily lives. And then there are things called semi-metals, which are way over here on the other side of this thing called basic metals, whatever the hell that is. And then we've got lanthanides and actinides, which we would include as metals. So are there 7 different groups of metals? And by the way, you're not going to be asked to repeat this on the midterm, just in case you're nervous. So let's take those 9 groups of elements from left to right and go through them. There's the alkali metals, the alkaline earths, the transition elements and metals, the other metals, the metalloids, the non-metals, the noble gases, the lanthanides, and the actinides. So 9 groups of elements seems reasonable. That maybe we run out of colors if we have more. So let's talk about the alkali metals. That's this first row. Lithium, sodium, potassium, rubidium, cesium, francium, which is radioactive. Lithium is definitely something that we'll be interested in. So, okay, we'll consider this to be a metal. Then the alkaline earths, beryllium, magnesium, calcium, strontium, barium. Yeah, we'll probably talk about some of those elements as well. Then we get into the transition elements, metals, which are sort of more classic metals, iron, chromium, vanadium, copper, those are definitely metals, and quite a few of those. And then the other metals are things like zinc. Well, that's a metal. Aluminum. Well, we're certainly going to talk about that. Gallium. Yeah. Cadmium, indium. Yeah. Tin. We're certainly going to talk about that. Mercury. It's kind of the funny metal because it's the only one that's sort of in its native state as a liquid. Lead. Certainly. Bismuth. Yeah. And then the metalloids. Boron, silicon, germanium, arsenic, antimony, and tellurium. Those are the metalloids. And then we have the non-metals. So these are things that we would say are not metals. But carbon, we're going to talk about carbon in graphite. That's an important, actually, is a critical metals in some classifications. Phosphorus, very important thing that we mine. Selenium. These things are important, but they're different somehow, and Matt's going to talk about that when he talks about electronegativity. And then the noble gases, and that's helium, neon, argon, krypton, xenon, and radon. So helium now is increasingly important. You could go back and say, well, wait, hydrogen, even though the astronomers don't consider that a metal, this is something that there's a lot of interest in mining. So shouldn't that be considered, in this class? And we don't talk about hydrogen in this class, or helium, or any of the rare gases. It's just, you run out of time in the semester. We'll definitely talk about the lanthanides. These are also known as the rare earth elements. So that's mostly this group. And it's very hard for people to remember these names: lanthanum, cerium, praseodymium, neodymium. Promethium doesn't exist. samarium, europium, gadolinium, terbium, dysprosium, ulmium, erbium, thulium, ytterbium, lutetium. You may remember Matt's lecture was talking about China cutting off the U.S. supply of rare earth elements, and there's a lot of interest in the United States and Canada, I'm sure, developing their own rare earth supplies. So we would definitely have to consider that. And then we've got the actinides, of which there's only two of them that occur in nature. That's thorium and uranium. Uranium is important for nuclear energy. So we're going to be talking about the whole damn periodic table, even though, in terms of what is a metal, even the chemist classification is too restrictive for us. So let's just review how we organize the elements in the periodic table. They're organized by increasing atomic number, which is the number of protons in the nucleus, as we just mentioned. So we go from lowest and lightest in the upper left to the heaviest in the lower right, which in nature would be not that one, uranium. So hydrogen's the lightest, uranium's the heaviest naturally occurring element. All of these others are things they exist, but they don't last very long. So they have lifetimes of a few seconds at most. So the horizontal rows are called the periods, right? That's the first period, second period, third period, fourth period, fifth period, sixth period. And the rare earths actually belong in here. So it's actually a sixth period, right? And the actinides belong in here. They're seventh period, okay? Now, the rows, these are every row is heavier than the one above it, right? So that has got to do with how big the atom is, and that'll become important when we talk about how minerals form. But as we go from right to left, the propensity of an element to interact with other elements changes, right? So elements in these rows, they all sort of behave similarly, like titanium behaves similar to zircon in a lot of ways. And zircon actually is almost indistinguishable in chemical behavior from hafnium, but that breaks down. You can see that, these elements in pink are somehow have a similar enough behavior in chemistry to be lumped together as metals, whereas these group, which is not a vertical row, it's not a group, it's kind of a diagonal thing. They behave similar enough to be called metalloids. So it's more complicated than the behavior of the elements being controlled just by where they are in rows or in groups on the periodic table. But the important thing is the elements within the same group share similar chemical properties due to having the same number of valence electrons, right? Valence refers to the electrons in the outermost shell, which that's where the chemistry happens. It is where one element will give up its valence electrons to another element. For example, hydrogen will give up its outermost electron, which is they only have one electron, to hydrogen, to oxygen to make the molecule H2O, water. So it's these valences that are particularly important that impose the first order organization of the elements from, in terms of more metallic behavior and less metallic behavior. All right, so given the many definitions of the term metal, what's the definition for the purposes of this class? So, reasonable question, and unfortunately, we do not have a reasonable answer. Basically, anything we get out of the ground except liquids and coal that we can process to use for economic activity that's what we're going to be calling a metal. So interestingly enough, the geosciences has divided this activity from other branches of activity. We've got paleontology and geophysics and, igneous petrology and all of these things. And then we have this subdiscipline called economic geology. And economic geology is the academic discipline that focuses on this effort. And so you could say we could call this class economic geology. I don't think that's as interesting a name as minerals and metals for sustainability, but and the other thing about economic geology is it specifically excludes oil, gas, and coal because those are somehow split off as petroleum geology or coal geology. But in fact, I mean, if you think about what's economic geology, it's really the study of things that we can get out of the ground and make money on. And so that should certainly include oil and gas and coal, but those industries are so different than the mining industry, which is focused on these things, that it makes more sense to divide the names according to, the similarity of the people that are working on the problem. Now, I asked ChatGPT, what are the best economic geology programs in the world? And it came back with this. Well, it's actually 9 because we had a late edition. So there's North America, Australia, and Europe seems to be the hotbeds. So Colorado School of Mines in the United States is there. University of Arizona's got an excellent program. Arizona's got a lot of mineral resources. Queen's University, Matt and you guys up there, you're at one of the preeminent economic geology programs in the world. UBC, University of British Columbia, there apparently is a mineral deposit research group unit there that, that makes it world class, and New Mexico Tech. In Australia, we get University of Tasmania has got an excellent group, the Code Center of Ore Deposits and Earth Sciences, and the University of Western Australia. Lots of ore deposits in Western Australia. In Europe, ETH Zurich, Zurich, Switzerland, and a UK university, Camborne School of Mines at the University of Exeter. So these are the top, at least from the point of view of AI, programs. And you might imagine that we're going to see a lot of examples for mines and mineral sorts of things from North America, Australia, and Europe, and fewer from other continents because of where the centers of research are. So let's talk very quickly about the atomic structure. Atoms consist of a central nucleus made up of nucleons surrounded by orbiting electrons. Nucleons are protons, which are positively charged nucleons, and neutrons are nucleons with no charge, and so they sit in the nucleus, and then the electrons orbit them like crazy planets all around. So now we have to sort of get into just a brief outline of where the electrons sit as we go through the periodic table from lighter to heavier. These will become important for bonding. So the shells are labeled K, which is the innermost, right? So this would be 2 electrons in the s orbital, and it's kind of confusing. This is the K shell, the L shell, the M shell, and the N shell, and then we've got these orbitals S, SP, SPD, SPDF. So that an element will have the same number of electrons as it has protons. So that's two electrons orbiting, by itself. That's going to be a helium. 2 plus 6 is 8. That's going to be oxygen. No, that's not. That's going to be a carbon, I think. And then out like this. But it's going to be these electrons out here that are going to be the valence electrons. All of these shells are being shown with all of their shells being filled. And what happens is the innermost ones get filled first, and then you go out, and as you go through periodic table, this outermost shell, whatever it is, whether it's S, P, D, or F, is going to be determining the valence. Those are where the valence electrons are. Okay? And if there's any questions, I hope you'll raise your hand, and Clint will see it and bring it to my attention. Okay, now the orbitals look different, and that influences the behavior of lots of things, which we're going to get into when Matt starts talking about bonding and complexes. So we've already said that the inner shells have more energy than the outer shells, and it's very difficult to remove an electron from an inner shell relative to the outer shell. But there are complications in the outer shells because they have complicated orbitals, as you can see. The s orbital has just spherical, the p orbital is this kind of funny figure 8, the d orbital is this strange clover leaf, and they have different energies, and that becomes important for ionization and bonding. And we're not going to have to get into the weeds here, but you do need to know that the chemistry is much more complicated in mineral deposits than we're going to be able to get into in detail, or that you'll be expected to remember. All right, so here's one way to look at what's going on in the periodic table. So the alkaline metals and the alkaline earths, we're filling the s orbitals, whether that's in the K shell or the L shell or the M shell or the N shell. That's what's happening. We're filling those s orbitals. And here we're filling the d orbitals going, across this part, right? And that's why there's none of these elements in the M shell, is because, to get to a d orbital, you've got to go through the S and the P, and then you get into the D. Now over here, we're filling the p orbitals, right? And then the noble gases, the rare gases, they're there because all of their orbitals are filled. They really have no valence electrons. That's why they don't bond with anything. And then down here, we have got the lanthanides and the actinides. We're filling the f orbitals, right? We didn't really look at the f orbitals because the d orbitals are complicated enough, but f orbitals are wild crazy. So that's explains the arrangement of the periodic table. Mass vertically and what's getting filled horizontally. All right. Excuse me, I got to turn that off. Should have turned my phone off originally. All right. All right. So like I said, f orbitals are complicated. So, there's the 7 f orbitals. So you can see here 1, 2, 3, 4, 5, 6, 7. And they each contain 2 electrons. So that means there's 14 electrons total in the f orbitals. So the filling of the 4f orbitals is why there are 14 rare earth elements, or lanthanides. So what we've got here is a way of depicting the orbital structure. So xenon is, let's go back to xenon. So xenon is here. So you basically, xenon is completely filled, s, d, and p orbitals. So we'll just say that's what, so we're adding on. We're not gonna say what is in all of these inner orbitals, right? So xenon is in all of these. It's basically the filled part of the electrons. But look what's happening between the D's and the S's and the F's. So lanthanum, you're filling, and lanthanum has got 1 D electron and a filled S cell. Now cerium has got 1 in an F orbital, 1 in the D orbital, 6 in the S. and then it goes back to you've gotten rid of the D and you just put 3 into the f orbitals, and it goes crazy like that until everything is completely filled up, and you've got 4f14 6s2. So it's complicated, but basically what that's telling you is, for some reason, all of these elements behave pretty similar. That's what you need to take home from this, right? These 14 rare earths, they behave geochemically very similar. So let's look at some examples. Here we've got copper, very important element, and its electron classification is 1s2, two electrons in the s shell, and then 2 electrons in the 2s orbital, and 6 electrons in the 2p shell, and then 3 in the 3s shell. I'm sorry, 2 in the 3s shell, 6 in the 3p shell, and then just 1 in this outer 4s orbital. That's the valence electron, right? You can see that it's the only one in there. So the behavior of that one electron makes copper special, because it'll give up that electron really easily. Now, uranium is another important element, but its filling of its orbitals is wild crazy. So it didn't even completely fill the 5f orbitals, and then stuck 1 in the 6d orbital, and then went out and finished the 7s orbitals. And so it's very complicated, but it's these differences in these orbitals that control the behavior of these different elements. No hands up there, Clint? You think they're in shock, or did I know I didn't explain
yes,
it
they are.
particularly? Okay. Does anybody need first aid administered? Because I'm not sure how we do that digitally, but okay. I'll keep mushing on, hope they recover afterwards. Luke.
How many elements do this where they start to fill out? It looks like the valence shell before inner shells are filled out.
Well, this is an interesting point. Obviously the hydrogen chemistry is really easy, right? Because there's only one electron. But as you go down here, we saw it wild crazy by the time we get to uranium. And it was pretty crazy even at copper, which is not even halfway through the periodic table. So it's really a question of what is the valence electron, and what Matt's going to teach us about is about ionization potential. How easy is it for an element to give up 1 electron? And we will see that's the critical point, is rather than trying to memorize all of these things, just say, I don't really care where I get the electron, whether it's from an s orbital or a p orbital, d orbital. Whatever's going to take it is going to take the one that requires the least energy, and that's captured by ionization potential. So the beauty of ionization potential, even though it seems confusing, is it's less confusing than this. So we're getting into the realm of physical chemistry, which is a field by itself that I am completely unqualified to teach. But if you want to learn more, believe you, there are people that can explain it to you better than I do.
Thank you.
All right. So as we said, the columns are arranged left to right to reflect the filling of the electron shells. So the period 1 filling the K shell. I'm sorry, period 1 this way, filling the K shell. Here we're filling the L shell, partly filling the M shell, finishing the M shell, and starting to fill the end shell. And period 5 is filling the O shell. So it gets complicated fast. So these, we can talk about first row, first period, second period, third period, right? And then the periods are sort of telling you about the filling of the shells, and then the rows, the rows are telling you about, how many electrons in the valence shell, or how many electrons in the outermost shell.